Morning Year 10. Today we're going to talk about electrical circuits. We're moving on to a new topic. So without further ado, let's get going. So make sure you're writing down what we're doing today as we go along. So starting with the structure of an atom. Now I know you've done that multiple times. We've talked about it in both your chemistry and your physics, but let's go through it once again. So inside the atom, we have got our nucleons, which are two different type of subatomic particles here, and some of them are positive with little pluses, and some of them are neutral, which have no charge at all. And I'm going to put the neutral ones with a blue dot in the center. So some are red, or some have a positive charge, and some have a neutral charge. Now, around the outside of that, we have got our electrons. This one has got 3 red dots, so it must have 3 electrons. Okay, let's try and label what we know about this. So the center we call the nucleus, and the nucleus only contains protons and neutrons. Around the outside we have our electrons, which have a mass of effectively 0. Remember, we have a special word for it we call negligible. Okay, very, very small. And it has a charge of -1. We have the nucleon, which is the red dot here. So this is the proton. And the proton has a mass of 1 and a charge of +1. And then we have the blue one over here, which is our neutron. And the neutron has got a mass the same as the proton of 1 and a charge of 0. Okay, so that is the structure of the atom. That's what we've got to start from, because every single atom in our circuit contains this structure. Now, the most important thing about this atom, especially when we're talking about electricity, is this electron here. Now, this electron here is the electron that can escape with very little extra energy, or extra kind of, energy. Let's go with energy. With a little extra energy, allowing it to move. Because remember that the electron is negative, the proton is positive. So this electron is being pulled to the center, but because it's so far away, this electron might be able to escape. And if it escapes, we call it a free electron. Now, the only chemicals that have free electrons are metals. The only atoms are metals. Things like iron, copper, slide that up a little bit for you. Iron, copper, magnesium, lithium, anything that is metallic will have free electrons, and those are really important in what we're going to talk about today. So those free electrons are actually what is going to move when it comes down to talking about current and talking about the way in which electricity can flow. So let's draw our first electrical circuit here. We're going to have what you probably know as a battery, but we're going to redefine that in a minute. We've got these wires. Now they should be drawn with a pencil and a ruler. Very important there's no gaps in your circuit apart from this one over here where the cell is. Let's have a simple bulb in here, and gap there, and we'll have a closed switch. Okay, yours should look neater than that, but this is a cell. This is what pushes our free electrons around the circuit. Now, if I was to zoom in to this wire here. Let's just make a little zoomy picture here for you. And this is before we've done anything else. Then inside of this wire, there are lots of free electrons. So here are my electrons in the wire. Obviously they're very, very small. There'd be a lot more than this, but that is just some of them to show you what's going on. So there's lots of free electrons. They're not really moving. As far as you're concerned right now, they're not moving at all. They're stationary. But once we put this cell in, this cell then starts to move those electrons. So it's almost like a push in the circuit, pushing the electrons round. So once we are closing the switch, or we are putting the cell into the circuit, these electrons start to move. And they start to move in this direction. Why do they start to move in this direction? Well, because this side is negative and this side is positive. So the direction of current, as we know, because it's lots of electrons moving, must go from negative to positive. And we call this one, we'll call it a number 1, but this type of current is our actual current, which for us is true because we know that electrons are negative. But the first person to come up with this idea of of current, didn't know about electrons, but did know about current and found out about something called animal electricity, actually believed, and probably quite rightly, but believed that it moved from positive to negative. We only know it goes the other way because those electrons are negative. But the person who first came up with it believed it would go from positive to negative, so go the opposite round the way of the circuit, and we call this conventional current. Now, unless I tell you otherwise, we are going to work with actual current, because actual current is really what is happening inside of the circuit. Okay, so we've used these words, current. What do they really mean? Maybe we should define current before we go any further. Well, current is the flow of electrons per second. Now, it doesn't have to be electrons. We could change this, and we'll kind of learn this when we come back to a bit of chemistry later on. But because in our wire it's electrons that move, that are our charged particles, then that is what we define current as. But anything that's charged could be our current. Now, another definition that we need to do, and we'll do this a bit more in the next lesson, but potential difference. And notice we're not calling it voltage anymore. We've called it voltage all the way up to now, but now we're going to go and call it potential difference. But potential difference is the push from the battery or cell moving the electrons around the circuit. So it moves the electrons around the circuit. So potential difference is what the cell is doing here, which is pushing all the electrons, because every wire is full of electrons. So it pushes one, which pushes all the other ones, because remember that negative charges will push away from each other. So push one and it'll push all these other ones away, all the way around the circuit until it gets back to the other side. Or actually, it's go the other way, because we know it's actual current, so it's going to go that way around the circuit because the electrons are pushing electrons. And potential difference is how much that push is. So the bigger the potential difference, the bigger the push around the circuit. And current is how many of those electrons are passing 1 point per second. So here we could have a measurement at that point here and measure how many electrons pass in 1 second, and that gives us an idea of the current. So the more electrons that pass, the greater the current, and the less electrons that pass, the lower the current. So that's like the fundamentals of what an electrical circuit is, and we can look at it in another way. So here is a piece of string, and I want you to imagine that these are all the electrons that are pushing each other inside of the circuit. Now, if I don't make this string move around in a circle, then there's no electrons moving. But if I start to push it, it's much easier when I've got another pair of hands in the classroom, but if I start to push it around the circuit, you can see, and certainly focus on the knot is starting to move, and that could just be one electron, but all of the electrons are moving. So you push one electron, so I'm pushing one part of the rope, then all of the rest of the rope will start moving. So this is a nice model of our electrical circuit. If this hand would then be the cell or the battery, which is pushing the electrons around, and the rope itself would be all of the electrons pushing themselves around the circuit itself. And obviously we could do it the other way if we thought we were going from negative to positive. If the thumb of my hand here was the negative side, then my electrons would be moving in this direction. Okay. So there are a few different circuit symbols that you are expected to know and be able to remember. So we're going to go through some of those now. This first one, which we've seen now in our circuits already, and you've heard me call it, is a cell. So this is one single unit that will have a potential difference to push my electrons around the circuit. If we do two cells with a dotted line between them, then this becomes a battery, because a battery is many cells put together. Let's move on. Again, you've seen this one this morning. We've got a switch. So two, what we would call terminals, these circles, with a line across them. This would be an open switch because there's a gap, so no electrons can flow, and a closed switch would just be a line straight across, but this is a switch. Okay, this is a filament, and this is important because later in this topic we'll come back to this, but this is a filament lamp. You might know it as a bulb, but it is just a lamp. We then have some symbols of some devices that we will use later on. This is an ammeter with an A in a circle, and this is a voltmeter with a V in a circle. And we'll come to those later on in the topic. We then have a line with a rectangle and another line. So there's two wires and a rectangle in the middle is a resistor. We can have another type of resistor which has got an arrow across it. This is a variable resistor. In other words, we can change it. So a variable resistor. We can have a resistor that has like a hockey stick through it. This is called a thermistor. Again, some of these will be important later on in the topic. We can have a resistor in a big circle with two arrows pointing towards it. This is called a light dependent resistor, otherwise known as an LDR. And again, we'll talk about that later on in this topic. And the final one you need to know is like a triangle with a bar on it, and this is called a diode. And diodes are really important. You might have heard of diodes before now because your mobile phones probably have lots of LEDs, light emitting diodes. Okay, really important to learn these, so make sure you go away and learn these, please. Okay, so let's look at the two different types of circuits that we can have. We have the series circuits and we have parallel circuits. So really important to know these two types. So series and parallel. Now a series circuit, an example, would be, let's go with a battery. And we'll have two bulbs. Two lamps. And we'll have a switch that's closed. There we go. That is a series circuit. So there is only one route around the circuit. So the electrons can only flow in one way around that circuit. They will start here and they will end here, and they can only go through this route here. So they will have to go through the switch, the bulb, the back to the battery. Okay. And if one lamp blows, then circuit will stop as current stops flowing. So if this bulb blows, for example, so we'll just take this bulb out, then you would end up with a gap in the circuit. Electrons can't jump that gap. They're unable to get from this point to this point. Therefore, no matter how hard we push at this side, those electrons aren't going to move. So those electrons stay stationary, so there is no current. Okay, so no matter how big the potential difference is here, pushing those electrons stay stationary and therefore can't jump the gap. And the same for the switch. If I open the switch, no matter how much potential difference I push from my battery, my electrons won't be able to jump that gap. Now there's a caveat to that, but let's leave it as is. That's what we need to understand so far. Later on in the topic, we might explain that in more depth. So the other type of circuit we can have is the parallel circuit. Now the parallel circuit, as the name implies, means that there are routes that are parallel to each other. So remember that something parallel in maths would look like that. They will never meet again, those two lines. Okay, so let's draw ourselves a parallel circuit. Remember, you're doing this in pencil with a ruler. So there is our battery. I'm going to have a switch and a bulb. I might have another switch here. My junction. And this is the parallel part. That was series. This bit now becomes parallel because now I have got two routes for my electrons to go. I have got the red route, which would be to go that way, back, and to the battery. Let's just put that all the way around. And I have got the green route. Just going to come out of the battery. It's going to come down, but now this way is going to go that way through the second bulb, come back up, and then follow the route back to the battery. So we can see red route goes around this way, green route goes around this way. So if this bulb was to blow, then in fact this bulb would carry on working. And that means that I could change and choose which of my two routes is going to stay connected depending upon which of these two switches I turn on or off. So if I have A and B, if I turn A off, so if I was to open this switch, then only B would light up. If I turn B off, then only A would light up if A was back on. And if I turn C off, so if I open this switch, then both of these won't flow because no electrons can come out of the battery itself. So a parallel circuit has multiple routes. Okay, and we actually call those branches. So you might come across that in one of my later videos. And each lamp can work independently of the others. So each lamp works independently of the others. So in other words, if lamp B was to blow, then lamp A would still work. Okay, so that's series and parallel circuits. Now we're going to have a look at some series and parallel circuits with a bit of an experiment. Now you might have already seen by going ahead in your booklet that you've got an experiment coming up, but let's talk you through how to do it. So you're going to go to the website that I've given you, which is called PhET, and PhET is really good for animations. Now, when you load up the PhET website, you're going to see it look like this. We've got a battery, we've got a wire, we've got a light bulb. That's all we're going to need, and a switch today. That's all we're going to need so far. So first of all, drag out a battery, then drag out a wire, and when you intersect the two circles, they'll connect, and you can drag your wire around and move it around as much as you want. So let's quickly make ourselves a series circuit. And you can have any number of wires coming off a circle itself. Let's add that bit there. We'll add a light bulb in here and a switch. Okay, so we'll connect you to there, and we'll connect those two there as well. So now I've got my battery, I've got my switch, which is open, so I'm not going to get any flow of current. We know that for the moment. And I've got my bulb. If I click my switch, then my bulb lights up. Unclick my switch, my bulb turns off. If I want to change what I'm connected to, I can either bin it, or I can click the circle and I can cut it, and that will split what I'm connected to. So for example, in your experiment, you will be asked to put multiple bulbs together. So here's 3, for example, and you're going to want to connect each bulb with the one next to it, and then close it and see what happens. Okay, so that's a series circuit, and if I was to go for a parallel circuit, you would just connect off the same branch. So let's just delete those two for the moment. We'll delete that one as well. We'll connect those two back up, put another light bulb into parallel, we'll have another switch, and then we'll have a wire connecting it all together. And if you close one, close the other, you'll see what happens. Now, you can change the amount of potential difference that's coming out of the battery by clicking on the battery, and you can change the direction. And in fact, if we change the direction, what we're going to see happen, well, the electrons flow the other way. Okay, so quite important that you have a look at that as well. Now, using this, I don't want to play around with any other buttons. Not today, we don't need to. You could play with the voltmeter, actually saying that, and the ammeter, you could have a play with them, but next time we'll use them properly. Don't change the wire resistivity, and don't change the battery resistance. You don't need that. If you click this button here, you'll also see a circuit diagram, so you can see what's going on. And if you want to take away the electrons, you can do that as well. So again, close them, and you can see what's going on. But you need to be on this view here with the battery, so the picture view, to see the brightness, and that's what I want you to investigate in your experiment for me. So the link will be in the booklet for you to do. Add your information to the booklet, or add it to another sheet of paper, and see if you can come up with an explanation and a description of what you're finding out. Okay, so let's go for a recap then of today's lesson. So we should have found out that free electrons, which we find in metals, we only find them in metals, are what move. Okay, so move in the wire. Why do they move? They move because the potential difference of the battery pushes the electrons, and we've learnt about conventional and actual current. The flow of free electrons, we'll go into this in more depth next time, but the flow of free electrons is the current. We've learned about different circuit symbols and the ones you need to know, so make sure you learn those. So circuit symbols, and we know that we need to use pencil and ruler when we're drawing circuits. And we've learned about two types of circuits. fact, there are only two types of circuits. You can't have any different ones. So two types of circuits. We've got series, which is one root. So there's one root around the circuit. And we've got parallel, which has multiple roots or branches.